Okay, here's a visual walkthrough of my new 140 megahertz interferometer setup. So I'll start over from this time. I'm going to start from the back side and move my way forward to the all the way up to the antenna. So here in the beginning is the computer, which is a i7 4790K CPU. I have a NVIDIA graphics card in there too, which is important for processing this data later on. But for the actual interferometer itself, a lot of the important details are right behind this monitor here, which is, first of all, I'll show you that you can see three Blade RF radios. So these are the software-defined radios that can sample up to 30 million samples per second IQ. So they have a 30 megahertz bandwidth, more or less. However, I'm sampling at 15 million samples per second for these tests. And if you look right here, you can see there is a splitter that's allowing for signals from one of the clocks to function as a master to drive the other two radios' clocks. And this allows for the signals to be synchronized in phase together between radios. Without that, you can't get any usable correlation. Signals that are going in the Blade RF are filtered by some Crystec SAW filters, which are right here. These are 835 megahertz SAW filters, which are used to slice off the local oscillator and image frequencies that come from the mixers, which are here. So these are mini circuits, ZFM 15 or ZFM 150 mixers. Doesn't really matter. They all work essentially the same. And you can see the IF is going to the Blade RFs. The local oscillator is provided by this Valon 5007 synthesizer, which is producing a 695 megahertz signal, which is filtered and then passed into the local oscillator ports in the mixer. RF signals are coming from here up these cables, running along here to some antenna craft, mass-mountable LNAs, which I'm just using here as actually tertiary amplifiers in my amplifier chain. So these have variable gain. They're pretty nice, and you can control your signal pretty conveniently. The signal that's coming, this is the amplifier set closest to the mixers, but the signals they are receiving have been filtered by a triplet of 140 megahertz SAW filters made by Triquint. And these SAW filters have a 20 megahertz bandwidth, about a 10 decibel insertion loss, and they give a really nice ultra clear notch that can clean up your signal dramatically, which is really critical if you're in a hostile RF environment, which is pretty much anywhere in the world, unless you happen to be lucky enough to live in, say, Western Australia. There is a set of amplifiers that are immediately upstream of the SAW filters, and these are some low noise amplifiers. Have two 2-meter LNAs that I purchased off of eBay, and then here's a mini circuits wideband LNA that I'm using here. And these LNAs have to have a good low noise figure at 140 megahertz because the signals that are coming from outside are traveling through a great deal of coax, approximately 500 feet of coax. So there's some serious loss of signal there, so you have to be able to pull that signal back up. I'm going to go ahead and stop there, and then in the next section I'll tell you more about the front end part of the system where the antennas are.